Welcome to the Chapter 4 lecture on variability. Variability is a quantitative measure, meaning it's numerical, of the degree to which scores in a distribution are spread out or clustered together. And variability really serves two purposes. First, it describes the distribution of scores. Second, it tells us how well an individual score represents the entire distribution. To give you a better idea of this, let's look at this distribution. The scores are not very spread out, so there is low variability. And because the scores are relatively close together, if you had any score, say 70, you know that other scores will be close to that. Comparing graphs, this distribution has a wide range of scores and high variability. And when variability is high, a singular score is not as representative of the sample. One measure of variability is range. Range is the difference between the largest x value and the smallest x value. For instance, take this group of scores. They're not in numerical order because they don't need to be, but the largest value is 9 and the smallest value is 4. 9 minus 4 is 5, and so the range is 5. While range is helpful for seeing how far scores span, it is sensitive to extreme scores. Take this example with scores spanning from 1 to 50. The range here would be 49, which is a huge number when the rest of the scores are just single digits. When there are extreme scores, the range doesn't tell us much about the sample. To avoid this issue, we can use the interquartile range, which is a range covered by the middle 50% of the distribution. Let's first break down that word interquartile. Inter means between, and quart means four. Therefore, this word means between four pieces. And that's essentially what we're examining here. If we were to have a normal distribution, we could divide it into 4 equal sections. And the points which separate these sections are our quartiles, labeled as Q1, Q2, and Q3. To find the interquartile range, or IQR for short, we need to find quartile 1 and then subtract it from quartile 3. There are 6 steps to finding the interquartile range. First, you put the numbers into numerical order. Second, you find the median of the full dataset. You can see how to do this in Chapter 3 if you need a refresher. Third, you split the data into lower and upper halves. Fourth, you find the median of the lower half. Fifth, you find the median of the upper half. And then sixth, you subtract the upper half from the lower half. If you recall from Chapter 3, you solve for the median differently depending on whether you have an odd or even number of scores. Because the interquartile range is based on medians, the same rules apply. For this example, say we have an odd number of test scores, and we want to find the interquartile range to see how students performed on the exam. First, we find the median, which again is the middle number. In this case, the median is 72. The median is our second quartile, and if you remember, we want the first and third quartiles, which means we can just exclude it. You can just cross it off. And what this does, it gives us a point of reference for our lower half and upper half of the distribution. Taking the lower half, the 58, 62, 65, and 70, we are just going to find the median of these numbers. Given that this leaves us with an even number of scores, remember that we need to take the average of the two middle scores, which in this case is 63.5. And this is our median for quartile 1. Then we are going to do the same thing on the other side. Take those numbers 75, 78, 80, and 85 and find the median, which is 79. This is our quartile 3. Again, the interquartile range is quartile 3 minus quartile 1, so 79 minus 63.5 is 15.5. This means that 50% of the exam scores span 15.5 points. There is some variability here. The scores aren't super close together, and as an instructor, I might guess that some people studied while others did not. Let's do the same thing, but with an even number of scores. Take the median of the scores available, which in this case is 76. There is no number to cross out in this case because it is even. So simply draw an imaginary line where this number would be. 76 would be between 74 and 78, so you are just drawing the line right down the middle. From here, you have the lower half and upper half of the distribution again. The median of the lower half is 68, and the median of the upper half is 84. So again, subtract 68 from 84, and you get 16. Here are two interquartile range practice problems for you to try. One has an odd number of scores, and the other has an even number of scores. Go ahead and pause to solve. The answer will be shown in 5 seconds. Okay, so for problem 1, the median is 72, the lower half median is 64, and the upper half median is 78. 78 minus 64 is 14. For problem 2, the median is 74, the lower half median is 66.5, and the upper half median is 84. 84 minus 66.5 is 17.5. As you know, range is sensitive to extreme scores. So one nice thing about the interquartile range is that it can be used to identify outliers, the extreme scores, in the dataset. This process is not described in the textbook, but it is important for this class. You can do this by multiplying 1.5 times the interquartile range and then identifying numbers beyond those scores. To give you a visualization of this, if we took that distribution with the quartiles shown earlier, the interquartile range is a range of this middle area. The outliers are those outside of this, closer to the tail ends of the distribution. Because we are looking at two separate sides of the distribution, we are going to have two slightly different equations for identifying outliers. For the lower bounds, the outliers on the left side of the graph, the equation is quartile 1 minus 1.5 times the interquartile range. For the upper bounds, the outliers on the right side of the graph, the equation is quartile 3 plus 1.5 times the interquartile range. Let's try this example. We have a list of scores 60, 62, 65, 68, 70, and 120. The interquartile range is 8, quartile 1 is 62, and quartile 3 is 70. For the lower bounds, we use the equation quartile 1 minus 1.5 times the interquartile range, and we just plug in those numbers. So we get 62 minus 1.5 times 8, or 62 minus 12 is 50. So anything under 50 is an outlier. On the other side of the distribution, we use the equation quartile 3 plus 1.5 times the interquartile range. Plugging in those numbers, that gives us 70 plus 12 is 82. So anything over 82 is an outlier. Taking these numbers, let's look at the scores provided. There are no numbers under 50, but there is one number over 82, and that's 120. So 120 is an outlier in this data set. Depending on the distribution, you may have one outlier, multiple outliers, or no outliers at all. It just depends on the variability of the scores. Here is an outlier practice problem for you to try. Go ahead and pause to solve. The answer will be shown in 5 seconds. So for the lower bound, we have 63 minus 1.5 times 15.5, which is 40. So anything under 40 is an outlier. For the upper bound, we have 79 plus 1.5 times 15.5, which is 102.5. So anything over 102.5 is an outlier. But looking at the scores, this data set does not have any outliers. One way to represent that interquartile range is with what's called a box and whisker plot, seen here. We start by plotting the median on the graph, which in this case is that little yellow line. From here, we have a box showing the span of scores from quartile 1 to quartile 3, that interquartile range. The lines on either side span to the lower and upper bounds, and any outliers are represented by circles outside of that range. This is a real box and whisker plot taken from Searchin et al. 2018, examining depression scores as a function of gender. What you can see from this graph is that men seem to have lower depression ratings than women. Women's median scores and interquartile ranges look to be greater than men's. And while some men do have greater depression scores, the ones who do are outliers. Having this information is important because it might change how we talk about and even treat depression symptoms in different people. While the range and interquartile range provide useful information, the most commonly used measure of variability is the standard deviation. Deviation itself is just the distance from the mean. It's the score minus the average. Say we have 5 scores, just 1, 2, 3, 4, and 5. The average of these numbers is 3. So deviation is taking that score and subtracting the average. The problem is that we cannot find the average distance from the mean by doing this. Because if we were to sum up the numbers, the -2, -1, 0, 1, and 2, we would just get 0. And this happens no matter what scores you have. So we solve this problem by first squaring each deviation value before averaging. Here's that same graph with each of those deviation values squared. Remember that when you are squaring numbers, you are multiplying them by themselves. So -2 times -2 is +4. -1 times -1 is 1, and so on. Once we do this, we have numbers we can work with because they no longer total to 0. So let's sum the values here. 4 plus 1 plus 0 plus 1 plus 4 is 10. And when we sum these squared values, we call this the sum of squares. And this is an important term to know because we will be referring back to this both now in this lecture and in future lectures. Once we have the sum of squares, we can find the variance, which is the mean squared deviation or the average squared distance from the mean. Essentially, we can say on average, this is how far the scores are spread out. But if you recall, we handle data from the population where all people of interest are included and samples where only a select few are included differently. We saw this with means, where mu was either lowercase and looked like a U, or capitalized and looking like an M. You'll notice the same differences here with one additional change to the sample equation. Starting with the population mean, we have lowercase sigma squared equals the sum of squares divided by n, which as a reminder is the number of scores. With the sample variance, we have s squared equals the sum of squares, again, same thing, just with the sample mean notation, divided by the number of scores minus 1. We have to subtract 1 here to correct for the bias in sample variability. Remember that the sample doesn't always precisely reflect the population. We'll do some practice problems here in a moment, but there is one last step. Once we get the population or sample variance, we can calculate the standard deviation and finally have that measure which describes the variation of the data. If you remember, we squared all of the original scores because the deviation originally equaled 0. So to find the standard deviation, we need to unsquare it, and we do that by finding the square root. So for the population standard deviation, sigma is just the square root of sigma squared, and this is the population variance. The sample standard deviation is the square root of S squared, which is the sample variance. Putting these steps together, here are the steps to finding the standard deviation. First, take the average of your scores and find the deviation by subtracting the average from each score. Square each of the scores and then sum them to find the sum of squares. Find the population or sample variance depending on who is in your study. The equations for this can be found on slide 17 of this lecture. Lastly, find the population or sample standard deviation by taking the square root of your variance. We'll walk through this first example together. Dr. Johnson is curious as to the ages of the members on his staff. The ages are 32, 28, 24, 28, 28, 31, 35, 29, and 26. What is the standard deviation of the staff's ages? This is a population because this is all of the people of interest. First, let's put our scores into a table and calculate our average. The average in this case is 29. So we subtract 29 from each score and square it. We add up the squared scores, which equals 86. Then we select our variance equation. Again, this is a population, so we go with the population variance. Remember that this is the sum of squares divided by the total number of scores. So this is 86 divided by 9, which is 9.56. We take the square root of that and then find that our standard deviation is 3.09. Here's a problem for you to try on your own. These are noon temperatures in degrees Celsius from a Canadian city in December from the 10 years between 1997 to 2006. The degrees were -5, -4, -1, -1, 0, -8, -5, -9, -13, and -24. What is the standard deviation of the temperature? Go ahead and pause to solve. The answer will be shown in 5 seconds. Okay, so as you can tell, we do not have every single temperature for the full 10 years, so we are working with a sample. Make your table. The average temperature is -7. Subtract that from each score and then square it. The sum of squares is 468. Take your sample variance and don't forget to subtract 1 in the denominator. S squared is 52. When you take the square root of that, you get 7.21 degrees. And that's all there is to it. If you have any questions, please let me know. But other than that, this is the end of the chapter, and I hope you all have a great rest of your day.